Hey guys, welcome back to Genius Learning. In this video, I want to look at classical mechanics problem. All right, so I want to show how to put a coordinate system on these two moving parts. So what we have is a hoop that's sliding down the plane, and the plane itself, which has a mass, is moving to the left. So as the hoop slides down, the plane is also sliding to the left as a result. All right, and they want us to find the Lagrangian of that system. So for this video, I'm not gonna do the entire Lagrangian. What I'm gonna do is I'm gonna set it up, and then in another video, I'll go ahead and derive the equations of motion, which get pretty tedious for this problem. But for now, I just wanna look at the coordinate system. So first, let's identify two things. We're gonna want the position of the disc or the hoop, whatever you want to call it. So the position of the disc, that means I want the x coordinate and I want the y coordinate of where the center of this disc is at. Okay, and then I also want the position, I guess I'll put it right here. So I also want the position of the plane, which is this entire thing, as it moves to the left. So here we have, we'll just write it here. So x is equal to, y is equal to. Okay, so let's start off with this angle here. So I like to start off with this angle here because I know that if this angle is alpha, then I can make in the angle in here, inside here, alpha. Or better yet, let's say I do this. From the tip of this radius, I'm gonna draw a straight line going this way. Okay, and so now, I hope it's clear that you can see this angle is the same thing as this angle. All right, and I'm also going to draw a line always from the center of the hoop straight down. So center of the hoop, I'm just going to go straight down like that. Okay, so also this angle in here is alpha. Okay, so we've identified the angles. All right, so these angles here are all the same. Perfect. Now let's see where the hoop is in relation to the plane. So let's look at that. Let's label the distance from the top of the plane to the bottom of the plane. Okay, so I'm just gonna draw a line going like that, up, and a line going up. And I'm gonna say that that entire distance there is gonna be L. All right, so I'm gonna have an arrow this way and an arrow this way that show that from this wall or from the bottom of the plane to the top of the plane is a distance of L. Okay, so let's also label a distance from the center of the hoop to the top of the plane. So I'm gonna call it S. It's an ugly looking S. Okay. S is from the center of the hoop all the way to the top of the plane. All right, so then you can imagine that this piece here is gonna be the entire length of L minus S. That's this space here. So this is gonna be L minus S, and that's gonna go from here to the bottom of the plane. All right, so you see how if I had this whole thing and then I subtract this thing from it, I'm only left with this piece here. So that's L minus S. This is S, and the entire thing is L. Okay, so we're looking pretty good. Now what else? Now let's do some trig. Okay, so we want the center of this hoop and we want the X position of it. So everything that goes here. Okay, so let's start drawing some lines and taking advantage of some trig properties and stuff like that. So we already drew a line down from the center of the hoop. Let's draw a line down from where the radius meets the plane. Okay, so I'm gonna draw a dotted line. Okay, so you can see I have like a little segment here now that I have to fill. All right, if I extend this down a little bit, I have another segment I have to fill, and then this last segment I have to fill in order for me to know the X position of where the center of the hoop is at. Okay, now let's do the same for the Y. So I have where the plane touches the hoop, and let's extend the line from the center of the hoop all the way to the outside. So center of the hoop, I hope this line is straight. All right, straight enough. So now I got a segment here and a segment here that will describe the center of the hoop. I got a segment, segment, segment that will describe the center of the hoop in the X and in the Y. All right, so let's label them and see what we get. So let's also close up one more piece. In the inside of this disc, I'm gonna draw a little line here, right? Making this a little triangle that we can use because now we have a 90-degree, right? And we can use some trig identities. So let's label stuff. Let's see what we got. We got opposite over hypotenuse. So this is gonna be R sine alpha. I'm gonna bring that R sine alpha down here. So we got R sine alpha. That's one of our segments that we needed. Okay, so I'll just draw a little arrow here. Perfect. Now this side here is gonna be what? It's gonna be adjacent over hypotenuse. So R cosine of alpha. And so I'm gonna take this piece right here and write it all the way over here, just like I did with the other one. R cosine of alpha. Perfect. All right, so we also drew this triangle here, right? So let's see what we can do with that. We got this, so this is tricky because this S distance right here is the same thing as this. So you can see that this distance here, we can label this part of the plane S. We're just bringing it down like that. Okay, so let's just do that so we don't confuse ourselves. So we're gonna label this piece here S. And now let's use this triangle. All right, so let's say opposite, which would be this entire thing over hypotenuse, right? But we don't need that piece because we don't need all the way to the top. All we need is the center of the hoop. So maybe let's look at this side right here. We got adjacent over hypotenuse. So we got S cosine alpha, and that goes from here to here. So if I project this down, I'm gonna have S cosine alpha. Okay, so I got two now. I'm missing this and I'm missing this one. All right, so now another triangle. So let me highlight these triangles just so we can see them better, because this is the reason why I would get these a little messed up before. So what we looked at right now was this triangle here. Okay, and that gave us this line here that we used. Okay, then we looked at this triangle in here. Well, we looked at this one first and then the other one. Okay, so then that gave us this here, and that gave us this over here, right? Because it gave us this side and this side. Now we're gonna look at another triangle. This one right here. They're tricky to spot out sometimes. So it's good to be a little neat when you're doing coordinate systems, especially with Lagrangians. All right, so you got that triangle there. Now, we don't want this whole side, right? Because we want the center of the hoop. So this side is fine. We want this side that can fill in this gap for us. So here, just like with this one, you have the hypotenuse came from up here down. This whole piece can come down here, so the L minus S. So let's do that. We got L minus S as our hypotenuse. All right, so now let's see what we got. We got opposite over hypotenuse. And so we're gonna get L minus S sine alpha. And that's this entire side here, right? Because L minus S is our radius or our hypotenuse here. So opposite over hypotenuse. We got this side, let's project this over here. And we have L minus S sine alpha, okay? And we're one step closer. So this triangle here now give us this. All right, so for the Y, we're done identifying where the center of the hoop is. We got this and this filled out. As for the X, we still have one piece missing, all right? And this is entirely up to you because since the plane is moving to the left, this coordinate that you assign here or label here, you have to understand that also changes with time. So let's say I assign it some random variable that I like to draw. Kind of looks like a Z. Okay, I'm gonna label it that. But this here changes with time. The S does not change with time because the S here is set in stone as far as like the distance goes. But when I solve for the equations of motion, I'll show in detail which ones we can take derivative of and which ones we can't. So for now, we just know that this one can change because the plane is moving. And now we have everything that we need, all right? So let's start with the position of the disc. What do we have? We have in the X direction, we have this funny Z looking thing plus S cosine alpha plus R sine alpha, all right? And so then that takes me to the center of the disc. I'm good to go. For the Y, I want to go to the center of the disc. So I'm going to do L minus S sine alpha plus R cosine alpha, which is this piece, all right? And I'm done for the position of the disc. Okay, so then after that, we take velocities and find the kinetic energy and the potential and stuff. But for this example, I just want to show how to get these position points, because actually that's the most important part. After that, if you take the wrong derivative and get the wrong velocities, the whole problem could be messed up. So the position of the plane, this one is pretty simple because in the X direction, all you have is this squiggly thing that represents the distance from 0 to the plane. So before we wanted the distance to the center of the hoop because that's what we're interested in. But now that we're doing the plane, we only want the distance from the center or the origin to the plane. So for X, it's simply that random letter. And then for the Y, it's sitting right on the Y on the 0, so that's gonna be 0. So that one's pretty easy. All right. So in another video, I'll show how to get the Lagrangian and work through the problems because this one is very involved with a lot of understanding of which derivatives we can and can't take. All right.